Okay, we need to get started today. So we will have an early quitting time today, which I'm sure is disappointing to very few of you. So before we do all the evaluations and everything that's coming at the end, we're going to start with moving on through chapter 9. So last time we talked about liquids and some of the intermolecular forces that are present in condensed phases, like liquids and solids. And we're not going to really do much more with liquids, but we're going to move on today to solids and start talking about some properties of those and really talk in detail about metals today. And then next time we're going to get into more aspects of the structural features of metals as well. So the first thing we need to do is define the types of solids that we have. We're going to talk about most of these in some detail. So let's get the definitions out of the way first. So the first type of solid that we want to talk about are amorphous solids. This is one that we're going to really deal with the least, because there's not a lot you can say about their structure because they don't really have a regular structure. So amorphous solids are solids that have no regular structure. All right, so we should recognize the big difference between a liquid and a solid is that in liquids, the molecules are in constant contact, but they are moving around each other in very regular motion. Solids, the atoms and molecules are more or less fixed in place. There's some vibration of them, but they're not really moving as we would think of in a gas or a liquid. For amorphous solids, the atoms and molecules that make up the solid are sort of just randomly oriented in all different directions. There's no regular array, there's no regular predictable structure there. It's just the components are randomly organized. So these solids can be made up of atoms and or molecules, and those atoms and molecules are arranged randomly. All right, there's a very common example of an amorphous solid that you've all dealt with in your regular life, which is glass. Okay, so glass is a solid, but it has no regular structure, so we call it amorphous. So there are probably others, but that's the most common one. What we're going to talk about more in this class, which is the other major type of solids, are called crystalline solids. So in this case, the components are arranged in very regular and predictable arrays. So it's a highly regular periodic fashion. All right, so we're going to talk in detail about crystalline structures starting next time. We're not going to see a lot of the details of these today, but what this means is that all the atoms and molecules are in a very regular ordered array. So if we have sodium chloride, for example, we know that at this position there's a sodium, and so many picometers or angstroms away from that is a chloride, and then so many picometers in the next is another sodium, and so on. We can know exactly where each ion is or each atom is in the structure depending on the type of solid that it is. So they're very regular arrays where the components are appear in a pattern basically. So then what do we call these patterns in more detail? So we have what's called the lattice and the unit cell. So the lattice is basically the pattern that's made up by the atoms and the molecules that are in the crystalline solid. So it's three-dimensional. All of the things we're talking about have three-dimensional structures. And the lattice is a 3D system of points where each point represents an atom or a molecule in the crystal. Now, technically speaking, lattices are infinite, and in our human world, we don't like to think of things that are on an infinite length scale. It's kind of hard to comprehend. So when we talk about crystal structures, as we're going to start doing next time, we don't usually consider the entire lattice, which, as I said, extends in all directions infinitely. What we think about is what's called the unit cell, which is the smallest piece of that lattice that's going to repeat in all directions. So the unit cell is the smallest repeating unit in a crystal, and that's what we're going to really talk about in detail in this course. Again, not starting until Friday, but we just want to get these definitions out now, since I'll use unit cell occasionally when describing these things. But the unit cell is the smallest repeating unit in a crystal. So when we have a lattice, which is the system of points in all directions, the lattice is generated by taking that unit cell and translating it in all directions. So we take that piece that we call the unit cell, we move it over one, we move it over and over in that direction, we move it in all directions. So when we move the lattice and translate it in all directions, that generates the lattice. Okay, so that's sort of the relationship between the two. All right, so again, with the example of sodium chloride, which is one of the first structures we'll talk about, the the unit cell is basically a cube that has some number of chloride ions and some number of sodium ions in it. We take that small cube and we move it in every single direction and repeat it over and over again, and that's going to generate the lattice for sodium chloride, which then, of course, generates those big crystals of salt that we're all familiar with when we put them on our food or use them to melt ice or whatever the case is. Okay, so those are some things about amorphous and crystalline solids. We're not going to talk a lot more about amorphous solids. Now, what we are going to talk about are crystalline solids, and within this category, there are sort of three subcategories that we'll have. And we're going to talk about the first two in a lot of detail, the third one not as much. So the first type is an atomic solid. And as the name implies, it's made up of one type of atom. So these are basically elemental solids, elemental crystalline solids that only have one type of atom in them. So the example that I show here is diamond, which is a form of carbon. Diamond is not the most stable form of carbon. So we learned in Chapter 7 that the standard state for carbon is carbon graphite, but diamond is another form of carbon where you have these regular repeating carbon atoms in all three directions. And this is sort of the one representation of the unit cell for diamond, the piece that repeats in all directions when you make a diamond. That brings up a sort of what I always thought was a funny point about the forms of carbon, which is we've probably all seen the commercials for jewelry that say a diamond is forever. Actually, graphite is more stable than diamond, so diamond is not forever, because if you leave it for a long enough time, it will convert to graphite. Now, fortunately, that time scale is much longer than any of us would be alive, so if you give your significant other a diamond, it's not going to turn into charcoal in the next few years or whatever. But a diamond is not forever. That commercial is a lie. Okay, so back to what I was going to say about diamond. This is an example of an atomic solid, which is just carbon atoms arranged in a regular three-dimensional array in all directions. Also, the ones that we're going to talk about even more, starting on Friday, are metals. So most metals are also atomic solids. All right, so mercury being the classic example that's not. Mercury is a liquid, but most metals that we have are crystalline atomic solids. And we're going to talk in detail about those structures starting on Friday. Another major type, which we'll talk about the structures of as well, are ionic solids. Okay, so we know now that most ionic compounds, or pretty much all ionic compounds that are the simple types, are solids, and they're going to be crystalline. And in this case, it's going to be the positive and negative ions that make up the lattice points. All right, so we have these regular repeating units of positive and negative ions. So in this case, the green could be the negative, the white could be positive, or vice versa. And we arrange those positive and negative ions in all directions to give a crystalline solid. And we're going to talk about a lot of these structures, and the ones that we'll see are going to be things like sodium chloride, zinc sulfide, MgCl2, etc. We've all seen ionic compounds a lot in this course, so we know what those are. and they tend to be crystalline solids. Now the last type that I'll introduce are called molecular solids. So this is going to be a solid that's a covalent compound. So it's made up of discrete molecules that are, and those are going to be the lattice points. So the lattice points are individual molecules in this case. Those are the points that repeat throughout space to make the crystal. And those molecules are going to be held together by intermolecular forces. So we talked about intermolecular forces last time, and whenever you have a covalent compound that exists as a crystalline solid, the molecules in that crystalline solid are held together by intermolecular forces. The classic example of this, which is depicted above, is ice, so frozen water. Okay, so when you have ice, you have this hexagonal arrays of water where we have hydrogen bonding interactions between all of the neighboring water molecules, which is holding those molecules in place and giving rise to the very rigid and very regular structure that we have in crystalline ice. All right, so those are the types of crystalline solids, just to be familiar with them. Like I said, the details of the structures are going to come a little bit later. What we want to talk about today are some properties of metals that are related to their structure and more specifically to their bonding. So before we get into detail about the structures of metals, let's talk about how are the metal atoms held together in a solid crystal of a metal. Okay, so what's the attraction, or what's the forces that are responsible for keeping those atoms in place? So for metallic bonding is what we call it. It's the type of bonding that holds metals together in their elemental form. We have what's called the electron C model, which is sort of used to describe the bonding in metals. All right, so when we have metal atoms held together, we don't have individual localized bonds between two neighboring atoms. We have delocalized electrons that are going to be covering a whole group of atoms. So as an example, if we have a group 1A metal, something like sodium, potassium, and so on, remember that the valence electron configuration for group 1A, we have one s electron, and that s electron is held pretty loosely. That's why these metals are so easy to ionize, because their outer electrons are held loosely. So when we have metal ions arranged into a solid form like we would in a metallic crystal, we can almost think of it for group 1A as that last electron is held very loosely, and so we have an array of cations. So all the valence electrons are still held tightly by each individual atom, but then all the core electrons are held tightly by each individual atom, but the valence electron, the s electron that's in the last outer subshell, is going to be delocalized over the whole thing. So we'll do this one. So basically I'm going to draw this sort of yellow smear here that just represents those valence electrons delocalized over all the atoms. Okay, so the valence electrons in metallic bonding are not held in place on any one atom or between any two atoms. They're delocalized over all the atoms. They're very loosely held, and they're just all over the place. And then if we go to group 2A, oh, we won't do that. Can't write with that. If we go to group 2A, these have two valence electrons, so now we can think of the arrangement as being a bunch of 2+ cations, where now we're going to have two loosely held valence electrons that end up delocalized among all the atoms. All right, so then again, this sort of smear of electron density where the valence electrons are delocalized over all the atoms and not precisely localized in any one particular atom in the structure. Okay, so just to give you an idea of what this picture means, this yellow that I've drawn, this yellow smear, is what is referred to as the sea of electrons. So that's all of those valence electrons that are not localized in a metallic crystal. And so all valence electrons are loosely held and delocalized in a metal. All All right, so because of this interesting bonding arrangement, we have some properties of metals that are directly related to that. So as we have always done in the chemistry course, we want to look at these sort of microscopic properties, the delocalization of electrons between among all the atoms, and try to understand how does that relate to some of their key properties. So if we look at the melting point of a metal, they tend to be moderate to high. So as I said, most metals are solids at room temperature. And if you want to melt the metal, you can do it at a reasonable temperature, but you still have to heat it up quite a bit. So they have moderate to high melting points. Now let's understand how the melting point changes as with the periodic trends. So if we move across a period, that's going to be going along a horizontal row in the periodic table, the melting point tends to increase. And this is especially easy to consider when you compare group 1 and group 2, which are right next to each other. Group 1 has one valence electron that's delocalized to hold all the atoms together. In group 2, you have two valence electrons, so you have more electrons holding everything together. You have more charge interactions, so the higher charge leads to the higher melting point. All right, so as I said, in group 2A, you can almost think of it as being 2 plus cations bound by the two valence electrons that are delocalized. And so because you have a higher charge in group 2A, you have stronger attractions between the cations and the sea of electrons, and that holds everything together more tightly, makes it more difficult to disrupt that structure and melt the metal. If we go down a group in the periodic table, so that's going to be starting at the top and going to the bottom within a single column, the melting point typically decreases. And this is because larger metal ions, as we've talked about, have weaker attractions to the electron C. All right, so in other words, the charge is more diffuse, so you have everything separated by a larger distance, and there's weaker attractions between them. Or another way to think about it is that the electrons are held less tightly, so it's a little bit easier to disrupt that structure because the electrons aren't holding on as tight to those metal nuclei. So there's two trends in melting point we want to be familiar with that deal with the metallic bonding and how it changes across the periodic table. If we talk about the boiling point for a metal, the boiling points for metals tend to be very high. So you have to go to really extreme temperatures to boil a metal. And that's because it's difficult to completely separate the cations from these valence electrons. Because in order to boil something, you have to completely break up all the atoms from each other. You're not just disrupting the structure, but you're really separating out all the atoms into the gas phase. And it's really difficult to do that. Okay, so you have to completely break them away from the others, and that's a challenge with metals because of those strong attractions between the nuclei and the core electrons with the valence electrons. All right, so in other words, when you go from, in the solid phase, the atoms are all held in place, and you have this sea of electrons kind of holding them together. If you want to melt it, you're going to disrupt that structure, but the metal nuclei, the positive charges, are still going to largely be in contact with the valence electrons in the liquid phase. There's just more, motion, more fluidity there. But then if you want to go from the liquid phase to the gas phase, you have to completely break all of those attractions. So in the liquid phase, you still have an attraction between the metal cations and the electron C, but in order to go to the gas phase, you have to completely break out an individual atom from that, which is hard to do. So the boiling points for metals tend to be very high. Let's also talk about what are called mechanical properties of metals. So there are the basic mechanical property of metal, which is what happens when you put a force on a metal. Metals are what are called malleable, which means we can bend them. All right, so if you want to do your best incredible Hawk impression and take a metal bar, if you try to break it, it's going to bend, but it's not going to break very easily. So they're very bendable, but difficult to break, and that's because of this electron C, the metal ions are not held in place too tightly. They can slide around a little bit because they're still able to maintain contact with the valence electrons, which are delocalized. And so you can think of it as the metal ions that make up the crystal lattice can sort of slide through the electron sea. Alright, so it's pretty easy to sort of distort the structure and still maintain contact of those metal cations with a valence electron, because the valence electrons don't have any sort of regular shape or array to them, so you can sort of slide the cations around, and that sort of relates to then how you're able to bend them on a macroscopic level. And then finally, electrical and thermal conductivity. Metals are good conductors of both heat and electricity. And this is because those electrons are loosely held. And that's especially true for the electroconductivity. We have these mobile electrons in a metal because they're not held in one place by the metal cations, they're delocalized over all of them. So because we have this electron mobility, we're able to transport charge very easily through a metal. Okay, so metals are good conductors of electricity as well. Alright, and then finally the last thing we're going to talk about today, which is going to set us up for what we do next time. We don't really need to know a lot of the details of what I'm going to tell you, but it is helpful just from a information standpoint to understand this. So next time we're going to start talking about the structure of crystalline solids. So that's just a brief introduction to some of the properties. Again, we don't have to go a lot of details. But the question is, how do we determine the structure of a crystalline solid? So how do we know exactly how far apart the atoms are, exactly what the shape of the unit cell is? What do we do experimentally to find that out? And so this is an experiment that I just did this morning, as it turns out. So we use this all the time to help us determine the structure of solids. And so it's called X-ray diffraction. And the idea here is that we take X-rays and we scatter them off of atoms. Alright, so you've probably learned about diffraction if you've ever taken physics. That's the idea that if you take electromagnetic radiation and you shine it onto a regular array of slits or points, it's going to go in all directions. And that's exactly what you're doing here. It's just that you're using X-rays, which have a very short wavelength, and you're using atoms as sort of the points that they're scattering off of, which are separated by a very small distance. So because the atoms are separated by a small distance, you need a small wavelength to be able to observe the diffraction. So when the X-rays scatter off, so basically you take an X-ray beam, you shine it on your crystal, and then the beams scatter off in all directions. At certain angles of diffraction, the two beams are going to constructively interfere, and that's when you're going to see them hitting your detector. So you have both constructive and destructive interference. Constructive interference is when two diffracted waves come together, where the crest and the troughs line up, and you get an increase in the intensity for those two waves as they interfere. And you also have destructive interference, where the two sort of cancel each other out. So the spots that we see so this is our detector plate where the scattered X-rays are going to hit that. It's kind of like a photographic plate. And when the scattered X-rays hit that, where we see these spots are the angles at which we have constructive interference. Okay, so when we have constructive interference, we detect X-ray signal on the spot, and we measure then the angles of these spots relative to the crystal itself, and that's going to give us information about the structure. Now, where exactly that comes from is what's called Bragg's law. And like I said, I don't expect to have any real detailed problems about this, but it is helpful to understand how we get this information. So for Bragg's law, we have an important parameter is lambda, which of course is the wavelength of the X-rays. We've talked about wavelength in the past. And essentially, when you have a crystal, you have regular planes of atoms. So all the atoms are in a regular array, and they form these flat planes, and you have different planes in the crystal. So the X-ray is going to come off, it's going to scatter off of one of the planes, or it's going to scatter off the other. And depending on the distance between those planes, at some angle, you're going to get constructive interference. So Bragg's law deals with the angle of the X-rays coming into the crystal and the distance between the two planes that they're scattering off of. And so the angle of incidence is what we call theta, what we abbreviate theta. That's the angle at which the X-ray is striking the crystal. And when we do an X-ray diffraction experiment, we purposely vary that angle over a bunch of different values to get as much information as we can. Then d is going to be the distance between planes of atoms. And then the Bragg equation, which a father and a son came up with together, so talk about, parental bonding, coming up with one of the key equations of X-ray diffraction together. I never did anything that fun with my dad. So the Bragg equation is, I just played baseball and stuff like that, is going to be m times lambda is 2d sine theta. So again, lambda is the wavelength of the X-ray, d is the distance between the two planes that the X-rays are diffracting off of, and theta is the angle that they come in on, and then n is going to be some integer value. So this is called the Bragg equation, and it sort of allows you to then determine, if you know the wavelength of your X-rays, which we do, if you know the angles at which we're seeing the positive interference, you can then measure the distance between the two planes in your crystal. You do that over all kinds of different angles with all kinds of complicated math that we're not going to talk about, and that allows you to get a very detailed three-dimensional picture of the crystal that you have. All right, so that's what we're going to end with today. We're going to do now the bonus quiz that I promised you we would have, followed by the evaluation. So let's get the clickers and everything set up. On this quiz, there's no right or wrong answer, so just answer it to the best of your ability. Please be honest and put some effort into it, because this will help me.